So fucking curious.
Hello, everybody. Thank you to everyone for coming out tonight. Sorry for the mass exodus of people from EAS to here. You can thank Alex Murtaugh for being a master manipulator and getting this room because it was booked by someone else, but now we're here. Also, thank you once again. SITTV is recording this so that way you guys can continue to study throughout the week, and anybody who can't be here can check that out. Hopefully they're going to have the video tomorrow. If not, definitely by the next day.
Most likely tomorrow.
Most likely tomorrow.
And trying to live stream it.
What?
I'm trying to live stream it right now. And
they're trying to live stream it right now. So if you can't see me that well, pull up on your phone. You can get a double. Where's it being live streamed?
SITTV at
YouTube.com/SITTV.
YouTube.com/SITTV.
Right now.
Okay. So, if you guys don't know who I am, that's my name, Jake Shozer. This is the SigEp MA221 Test 3 review. If you guys didn't know where you were, just in case. And these are the 4 topics we're going to be going over. So you might be thinking, cool, there's only 4 topics on this test. But then you look at what the topics are and you're like, oh no, there's 4 topics on this test. And normally at this point I'll ask which of these is the worst, which ones we have absolutely no clue on, but I'm not even going to ask that question because I know the answer is going to be all of them. So I'll plug that also. The review notes form, fill out that form. I also sent the link in the GroupMe page. Anybody who fills that out, it's just name and email. I will send all of the review notes to you guys after the review tonight by the time I go to sleep. Yeah, and then I have a bunch of old exams. This test, they changed up slightly last semester in terms of the topics that were on it. So there used to be more Laplace on this test, and you didn't have both Fourier series and separation. They would switch like one semester, another semester. But last semester they moved more Laplace to the second test, so it was 1 question on each of these 4 topics for the final, or for the test 3. And you can see that in the spring 19 test that I have that I'll send out the notes after. So I say that because the most recent test will be a good layout for what I'm guessing that you're going to have this semester, but there's still good examples on other tests that you could look at. Does all of that sound good? Does anyone have any questions before we start? Okay. So we're going to take a nice deep breath in. We did some running around to get here. People are waiting outside the EAS for a while. It's going to calm down a little bit before we jump into our unit 7. Okay. So unit step functions. What is the purpose of them? Why do we care about them? So the first thing is we like them because they're used to take the Laplace transform of a piecewise function. They're used to take the Laplace transform of a piecewise function. So that's how they fit into what we're doing in this class with all of our Laplace transforms. And the idea of what a unit step function is, I'll do a little deviation from what's on the notes. Just because I learned this last semester when I was in Mech and Control Systems class, and I think it's pretty cool. The idea of this unit step function, this u of t, this is some special term, some special function that when your time is greater than 0, it's equal to 1. Or I guess I should do it the other way. When your time is less than 0, it's equal to 0. And when your time is greater than or equal to 0, it's equal to 1. That's all that this unit step function means. It says, I'm off until I hit time equals 0. At this time, I jump up to 1, and then I stay there forever. So it looks something like this. Where we have, it's at 0, we hit time 0, it jumps up to a value of 1, and it stays there forever. But we don't use this just u of t a lot, we use u of t minus something. So now what does that mean? Well, this u of, say, t minus 2, all this does is, where we had a t here, we are now replacing with t minus 2. So we do the exact same thing on the other side. So it's equal to 0 when t minus 2 is less than 0, and it's equal to 1 when t minus 2 is greater than or equal to 0. Now you can rewrite these as just when t is less than positive 2 and when t is greater than or equal to positive 2. So now, what's the result? What does this graph look like now? Well, now we have something that is equal to 0 until you get to this point 2, and then it turns on to 1, and it stays like that forever. So how does this help us in the problems that we're doing? Well, if you're given something like some function, we'll call it just t, that is on between 0 and 2, I know I'm going to write this as t times u of t minus u of t minus 2. And you think about the intervals that we have. We could have something that's less than 0. So if our t is less than 0, well, if t is less than 0, then I know that my u of t is going to be 0. And I know that my u of t minus 2 is going to be 0. So if I have 0 minus 0, this whole thing evaluates to 0, which means t times 0 is 0, which means my function's off. I have nothing because I haven't turned on yet. Then if I look at the region where I have some t value between 0 and 2, well now I'm in here. So I know that my u of t term is 1, and I know that my u of t minus 2 is still 0, because I'm in this region between 0 and 2. Right? Kind of drawing like a little t-chart here. So now, in this region, I know that the thing inside the parentheses is going to be equal to 1. When I multiply that by t, I now get just that t, because this is just saying that my function between 0 and 2 is equal to t. And now, if I look at some region where t is greater than 2, I know that my u of t term is still on, right? Because now I'm looking all the way out here. My u of t term is on, which means it's 1. And my u of t minus 2 term is now also on. So I have 1 minus 1, which equals 0, which now, when I multiply the t times 0, it's now back to 0 and it's off. So this is what's happening when we're turning our functions on and off with all of our unit step function stuff that's going on. You don't need to fully conceptually understand all this stuff. I just like this because it helps people to get a better feeling of what the hell does it mean when I'm writing something like this. Well, this is the actual stuff that's going on in the graphs that are taking place. Did this make sense to anyone? Okay, cool. And I saw at least a couple head nods, so it was definitely worth it. Because I think this is context that you don't normally get in the class that kind of brings some stuff together of what the hell is the things I'm writing down, what do they actually mean. So, now that we know that stuff a little bit, and to have an understanding of what's going on, we can jump into a problem. Like this. So the first thing that we'll do is I'll jump into this one first. So say if we have some function of t that's 3 e to the t when 0 is, or when t is between 0 and 2, and then it's 0 when t is greater than 2. Now a problem like this will say, take the Laplace transform of f of t. So in order to do that, the first thing that you have to do, we said that unit step function is used to take the Laplace transform of a piecewise function. And we have a piecewise function. So we need to first write this out in one equation that uses unit step. So I know that my f of t can now be written like this. I'm going to take my first piece of the function, which is 3e to the t, and multiply by u of t minus where the function turns on, which is 0, and then subtract u of t minus 2, because that's where this function turns off. So it turns on at 0 and it turns off at 2. Most of the time we'll just write this u of t minus 0 as u of t because it's the same thing. And then I need to add on my next function, which is 0, times u of t minus where it turns off, which is 2. Or where it turns on, sorry, which is 2. And it never turns off, right? So I don't have to do a minus u of t minus something, because that doesn't exist. It stays like that forever. Now in this problem, since we have 0 times something, we can see that this is just going to go to 0 anyway, so we don't have to worry about it. But now we're looking at this term here. And I need to take the Laplace transform of it. So once I have it written out in this function, now I'm going to distribute it out so that way it gets a little bit more simple. So let's distribute this 3e to the t to both of these unit step terms. So we now have 3e to the t times u of t minus 3e to the t times u of t minus 2. So we have this. And you'll see, if you go get a Laplace transform table for this test again, and you'll see something on there that says if you have f of t minus a times u of t minus a, that transforms into e to the negative as times capital F of s. So what does that mean? That says if I have, we know that we're using unit steps because we have this u of t minus a. This says if I have a sum step t minus a being multiplied by a function where t is also in terms of that t minus a, then I can do this transform where it becomes e to the negative as times f of s. Notice that this isn't f of s minus a. So this f of s, all that this is the Laplace transform of f of t, not the Laplace transform of f of t minus a. So what that means is, if I can get something into this form, I take the Laplace transform, ignoring the fact that I have this as a t minus a, pretend it's just a t, to get my f of s. Then in order to account for that unit step function, I just multiply by that e to the negative as. If that made sense, great. If it didn't, we're now going to do it in the problem, so hopefully it will make sense. The first thing I need to do is I need to get it in the form of that f of t minus a times u of t minus a. So I look at my first term, and my t minus a is just t, and in my function I have just t, so we're good. I look at this second term, and my u of t minus a is t minus 2, which means everywhere in this function that I see a t, it needs to be t minus 2. Is that the case?
No.
No. Because that t is t. It's not t minus 2. So now, I need to do some manipulation in order to make this be a t minus 2 without changing its value. So things that you're allowed to do are you're allowed to add constants, but then you then have to also subtract them. You're allowed to multiply by constants, but you also then have to divide by them, so that way it cancels out. So the way that I like to do this is we know right now we have 3e to the t, and we want it to be in the format of 3e to the t minus 2. But right now, these two sides aren't equal. I need to do something to this left side, or rather, I need to do something to this right side, so that way it equals back to 3e to the t. So what we need to figure out is how did I change this value by adding that extra minus 2. So let's break this down a little bit. We know that 3 to the t minus e to the t minus 2 is really just 3e to the t times e to the minus 2. knowing our exponent rules, which I know we all love so much. So I now look and see, well, how is the right side now different than the left side? Well, I multiply by e to the minus 2. So in order to counteract that, I need to now multiply by an e squared. Because now this right side is equal to the left side again. So bringing it all back and I can now just bring this e to the minus 2 up. Or sorry, e to the positive 2 up. And I now know that 3e to the t is equal to 3e to the t minus 2 times e squared. And since this e squared is a constant, there's no t's in there, I don't have to worry about doing any further manipulations. I'm good to go already. So, I can now take this and plug it in for my 3e to the t over here. So, rewriting this next line, we have 3e to the t times u of t minus 3e squared e to the t minus 2 times u of t minus 2. And now, all of my t minus a terms match. So, now I can use this transform. I can take the Laplace transform because I'm in the correct format that matches what's on the table. So, I know that what that says is I can take the Laplace transform pretending that my t minus a is just a t, ignoring the fact that I have that unit step. So, I'm going to take the Laplace transform of 3e to the t. We look on the back of our Laplace transform table, and this says that it becomes 3 over s minus a, where I know that a is the coefficient in front of that, so it's 1. So this becomes 3 over s minus 1. And then I multiply by e to the negative as, where I know that my a right here is 0, so it's e to the 0s, and I know that anything to the 0 power is just going to become 1. So that will eventually go away. But now on to the harder side is, again, I take the Laplace transform, pretending that this t minus a term is just a t. So this is really just e to the t again. And if that's just e to the t, I know that it's just going to be the constant, which is now 3e squared, over s minus 1, times e to the negative as, so e to the negative 2s. And this is now my capital, this is now the Laplace transform of f of t. So you can simplify this down a little bit. So all I'll do is this e to the 0s will go to 1. So we'll be left with 3 over s minus 1 minus 3e squared over s minus 1 times e to the negative 2s. Question.
So why didn't the 3 or the e to the second part of that cancel out when you added?
You're saying why didn't this cancel out when I multiply by this?
Well, not that.
Up here. So if I wanted to simplify this down, it would cancel out. But I'm intentionally making it more complicated because I want this to be in the format of e to the t minus 2 because the t minus 2 needs to match n. So I'm pulling out this e squared constant in front so that I can have e to the t minus 2 because it being in this format allows me to do that with Laplace transform. If this was just e to the t times u of t minus 2, I could not do that with Laplace transform. So, that's an important question. One thing the way that the terminology that they use is really inconvenient because there's two different A's that we're dealing with. We're dealing with one A where in this Laplace transform, we're told that it's e to the AT transforms into 1 over s minus a. But then we're also told that when we have this Laplace transform of u of t minus a, it's e to the negative as. This a and this a are different a's. So be careful with that. Because one a comes from the Laplace transform, comes from the exponent of your e term. In this case, it's e to the 1t. And the other a comes from inside of your unit step function where it's u of t minus a. Inconvenient, but just something to make sure you're aware of.
How did you recognize that it was in that form of f of t minus a, u of t minus a? So I just don't see that in the...
You're saying, how did I recognize that this is in that form?
Yeah, but starting from the top though.
Starting from here? Or from here?
From there, yeah.
Starting from here, I just distribute this out. So I'm going to do that every time. And I get to this line. And I look and say, it's governed by whatever your unit step function turns on. So here it's u of t, here it's u of t minus 2. That means everything in the terms being multiplied by each unit step, I have to have all of my t's in the parentheses t minus 2. So here it's just t, it doesn't really matter. But here I have t minus 2. I need this to be a parentheses t minus 2, and it's not. So then I have to do the manipulations to get it to be in that. Yeah.
On the second to last step, you just replace t minus 2 with t, so you can be able to define a Laplace transformer.
You say get from here to here.
From there to the next step.
From this step to this step?
Bingo.
Yes, I took Laplace transform. This one has been multiplied. This one, pretending that this was just t. And then I accounted for the fact that it's not t, but multiplied by e to the negative. Yes.
Can you just elaborate on why the two A's are different?
The two A's are different because they're coming from different parts of the formula. So this A in the denominator, and if you want, you can think of it as A and B. Think of them as two different values. They just happen to use the same letter to represent both like Laplace transform. Because this A that comes in your this. So this A, this one right here, that A is the same as here and here, which shows up there. Whereas here we have like a T minus 2. This A is the same as that, the same as that, it's the same as that. Yeah, it's just like right out of the big FS. The big FS is so each of these are things like that.
Just took those bars are equal to t minus 2. Where would the negative 2 go? No, I'm talking about 3e squared times e to the minus 2. Oh, that was separate. Okay, that's why I'm glad you said that.
We need the Laplace minus 2.
Yeah. Okay, the t minus 2 is minus 2 t minus 2 is equal to that. Yeah, if we're equal, so because you would multiply the 2 guys.
Yeah.
Up top, if it's t minus a, treat the f t minus a as a t, and multiply by e to the negative a.
So I get to kind of something.
So the question was, how do you handle if it's something that's more complicated than this? And all of the steps that I did follow the same exact steps. So first, these lines will be one line. Like function times 2 of t minus squared turns on, minus u of t minus where it turns on.
Alright.
Then the next step,
I'll keep it in mind. So probably not going to put on.
then put everything into the correct format, and then you took the Laplace transform. So you have more terms here, it's still be the same thing, it'd be the same steps. One is defined by dividing by 1, it's the same thing.
There's only one more thing that are. That might be that.
Yes.
I haven't seen that. Either the left and right I can sit back up on in front of it.
Are there any other questions on taking the Laplace transform?
I'm putting it on.
If not, we'll go to the inverse transform.
Yeah. Always keep the extra like It's annoying.
So it's ready for the next one.
Yeah.
So we're still dealing with unit step. Over here, we went from the time domain, so we went from t's to give ourselves s's. Now, we're going to go from s's, and we're going to do the inverse transform, and we're going to end up with t's.
Yes, that is an equal.
So the way that I've seen them ask these types of questions, they sometimes will give a full problem where it gives it in unit step and says, solve this differential equation, where you have to do both of these in one part. And in other problems, on other tests, they break it up into parts, where they'll say, just take the Laplace transform of this, and they'll start like a part, or question 1b will be, here's something completely different, find the inverse transform of this. And each one will be worth 10 points, or 15 and 10, however they break it up. So, we have this, and we need to take the inverse transform. So, the first thing in your mind, you should say, okay, I know that I'm going to need to eventually use unit step function. Why? What in here tells me unit step function? E to the negative 2s. Because I know that the only time I can get something where I have an e to a power that includes s is from this transform, which means I'm using unit step functions. So, okay, I now know that I need to use unit step functions. What do I actually do to solve this problem? Where do we start? Partial fractions?
Yep.
So this one's actually not going to involve partial fractions, but the first thing that would even take us to get to partial fractions is we want to try and factor our denominator so we can break it up into multiple terms, right? Because I don't like having two terms in my numerator, I want to separate this out into two fractions. So let's see if we can do partial fractions. Let's factor this denominator. So s squared plus 4s plus 8. I know that this is going to be the sum of two numbers, that's the product of two numbers, and that's going to be imaginary. So, you should see something like this, and you should have seen it a couple times by now, whether it was on homeworks or on gates or whatever it was. Where you try and factor that denominator, and it turns out to be imaginary. It's going to be pretty common, and I will almost guarantee you'll have something like this on the test because they very much like to ask it. When you have that denominator that can't be factored, you're going to have to use your completing the square. So what that means is we look at this term, we look at the term in front of our s, so I'm going to call that my b, so b is equal to 4. I'm going to do b divided by 2 and squared. So in this case, b divided by 2 is 4 divided by 2. Squared is going to give us 4. And the whole reason why I'm completing the square is because this method will allow me to break this down into a s plus something squared, which will make it turn into something much nicer. So, what I do is I'm going to add 4 right here. But I can't just change the value of what I have. I can't just add 4 because now this fraction is different than what it started at. So I need to also subtract 4. But the place, like I'm specifically adding 4 here and subtracting 4 at the end because I can now break it up like this. Where I know that s squared plus 4s plus 4 can be rewritten as s plus 2 squared. And I now have 8 minus 4, which can just be rewritten as 4. So this is now my new denominator of s plus 2 squared plus 4. So let's rewrite what we were given using that new denominator. So I now have s plus e to the negative 2s over s plus 2 squared plus 4. So I know I'm not going to be using partial fractions because that does not look like partial fractions. But that should look like something else that, assuming you did your homework, or at least paid attention to it as you were submitting it, this should look really familiar. And that's the benefit of homework, is if you would recognize this. Where I have something in the denominator, where I have a term with s squared plus a constant, where that constant is a perfect square. And this rings in the bells in my head of the Laplace transform of a cosine and a sine function. Because I know that the Laplace transform, I have cosine of bt, this turns into s over s squared plus b squared. And if I have sine of bt, it turns into b over s squared plus b squared. So that denominator looks close. It's not exactly what we have. And depending on the form of the Laplace transform table they give you, they might be nice, they might be a little bit mean. Sometimes they give you the general format, sometimes they give you the specific format. I'll give you the specific one because on other times they'll give you the exact, when you have e to the at cosine of bt, so you just take this and you multiply by e to the at, it changes it ever so slightly, where our numerator is now s minus a, and we have s minus a squared plus b squared. And the same thing when we do our e to the at times sine of bt, we get b over s minus a squared plus b squared. So now, this should really be looking familiar because this denominator matches that format. That's the denominator in those formats.
They'll give us those up to
Maybe. They'll definitely give you these, and they'll give you either these, or they'll give you e to the at times f of t transforms into f of s minus a. They'll give you, this is just the general format of that. Where this bottom one is saying, if you have an e to the at times some function, you take the Laplace transform of that function, but instead of s, you plug in s minus a. And notice that that's all that we did. All that I did here was, everywhere that I had an s up top, I just plugged in s minus a. So they'll give you, if they're nice, they'll give you these. If they're mean, they'll give you this bottom one. You have to understand how that applies. But when I send out the test after the review, you can see the exact Laplace transform table. But it's normally the same list that you got for the test 2. with, like, I don't think you had your sines and cosines on test 2, so these add on. As for when you're doing your inverse Laplace transforms, they could give you other stuff, but they love to ask you how many sine, cosine ones. Yeah.
The Laplace table, for example, with all those.
It has all of these? Oh, there you go. It's got all. So you can pick and choose what you want, if they give you the same one. But now that we know this, we can now come back to the problem that we have and see what we're going to do. So now, I still don't like multiple things in my numerator, so I'm going to break it up, what my high school teacher called sharing the love. So you break up into two, and it's a little hard, you know? So we have s over s plus 2 squared plus 4 plus e to the minus 2s over s plus 2 squared plus 4. So now what do we do? Do either of these match anything up there?
No. One.
They can. Right now they don't. Because right here I have an s over s minus a plus b squared. Or s minus a squared plus b squared. But I need it to be, I know this is looking like my cosine format because I have an s in the numerator, but I need it to be s minus a. So what I'm going to do, I need this to be s minus a, where I know that a is a negative 2, right? It's s plus 2. So I can just add that, but I can't change the value of what I have. So I need to do minus 2 over s plus 2 squared plus 4. Right? Because when I add 2 here, I need to subtract that same 2 over that denominator so I don't change the overall value.
What's preventing you from just doing that to the first fraction?
Up here,
Nope, not the one that you wrote in black. Yeah.
just doing s plus 2 minus 2.
Yeah.
You could do that, but we want this s plus, so I could have written minus 2 right here, but I need to break out this s plus 2 separately because this overall thing that I certainly agree now fits one of my formats.
All right.
So I want to break out this minus 2 over that denominator, so I just did that right from the start.
All right.
So now, I can take the Laplace transform of this.
Yep.
Okay, that's good. Over here, can I take the Laplace transform of this?
Yeah. No.
I can, because I know that it needs to be in this format.
Yep.
I know since I have a constant in the numerator, I'm looking at my sine transform, and it says I have to have a b over s minus a squared plus b squared. And I know that b is 2, so I know that that one's good. But now I gotta look at this middle term. And this, e to the negative 2s term, I know that all that's gonna do is tell it's gonna be a unit step function. So I'm actually gonna bring that out after. So it's just gonna be e to the minus 2s with a 1 in the numerator. Right? All I did was just bring that, multiply it out after, it doesn't change the value of it. But looking at what I have here, this still doesn't fit one of the transforms. Because I know I have a constant in the numerator. Well, a constant in the numerator has to be b, which means it needs to be 2. So one thing I'll say is doing Laplace transform, coefficients are your best friend. Because I can pull out any coefficient in front of the Laplace transform to multiply by this and make the Laplace transform whatever I want it to, the constant, whatever I want it to be. So what that means is, I know I need this numerator to be 2. So what I can do is I can pull out a 1/2 as a coefficient and make the numerator 2. So I can pull out a 1/2 coefficient and make the numerator 2. Because 1/2 times 2 is still 1, which is what I started with. But now, this thing in the green fits one of my Laplace transforms. Question?
Would it need to be minus 2?
I'm not pulling out a number. I'm not pulling out like I'm not adding or subtracting. I'm factoring it out.
Yeah, but wouldn't it still need to be -2 because it's s plus 2 on the bottom? In that format, it's s minus a.
No, because the numerator has to be b. And b we find out from that constant here. So
Okay.
this plus 4 is my b squared, which means my b term is 2.
Yes.
Or a, which is in here, is -2. But this, the 2 in the numerator, comes from my b squared, which is 4. It's annoying how in this problem they made both a and b 2.
Okay.
But now all 3 of these are in formats that I can take my inverse transform. So let's go ahead and do that. If I have s minus 2 over s minus 2 squared plus b squared, or plus 4, I know I'm in this format right here. So this turns into e to the negative 2t, because my negative 2 comes from right here, times cosine of bt, so cosine of 2t, because my b, this right here, is b squared. So b comes down to that cosine. So that's the first one. I'm going to do the third one next, because this is the one that doesn't involve unit step. So I now have a negative 2 over s plus 2 squared plus 4. I know I'm in this range, or this transform, so it's e to the negative 2t times sine of 2t. And now I just need to look at this middle term, where I know this is going to be a plus 1/2, this will be a minus. Now, I need to worry about the fact that I have a unit step function. So when you're doing the inverse transform, so I'm going from here to there, all I'm going to do is, I'm going to go from this f of s directly to f of t. So I'm going to completely ignore the fact that there is a unit step function term in there. I'm just going to take the inverse transform like I normally would. So, the way that I normally would, this is just the same thing I did over here. So it's e to the negative 2t sine of 2t. And after I get that f of t, I know that it's not really f of t, it's f of t minus a. So now I have to account for the fact that I have that unit step function by just plugging in t minus a everywhere that I have a t. I don't need to worry about doing that fancy conversion stuff over here. All I have to do is just plug it back in and it's done. Question?
Yeah, if you were to do that, the third one, and you had it as plus, and then top was -2, so your b would be -2, which then could you do the sine of and add that term? Instead of subtract it?
You're saying if this was sine of like plus e to the negative 2t sine of the negative 2t? Since this was just plus negative 2? I'm going to go with no, just because I know that those aren't the same value. So I know that sine of negative 2t and sine of 2t are not the same. Sine of 2t is not the same thing as negative sine It should be fine. I think that would be okay.
Right a little bigger.
Because I think that sine of negative t is the same thing as negative sine of t. So you should be okay. But I'm not quite done yet. I plugged in that t minus 2. The last thing I have to do is remember to multiply that term by u of t minus a. So, let me rewrite the entire answer. It's organized. We're going to have e to the negative 2t cosine of 2t plus 1/2 e to the negative 2t minus 2 sine of 2 times t minus 2 all of that is times u of t minus 2 minus e to the negative 2t sine of 2t. And this whole thing is your f of t.
Question.
Yes.
For the exam, if we're pinched for time, do you still do that problem for last? Because as it is, it took a long time just to get to that answer. So we only have 50 minutes to do about one problem for each.
Yeah, you're gonna probably run out of time this test. Say that right now. Unless they change it up to what they did last semester, these are 4 problems, but they all take time. So, however you want to approach that, I'll just warn you going in. Question.
So did he solve there?
Yes.
The same thing that we're going to see here. Just now. Shows up right here. Just like we use bolts in this problem. Slide down a little bit. I heard you say y is plus 2. You're saying in here, because this format is e to the minus as. So in my unit step, e to the minus as, a is equal to positive 2. Yeah.
So in the review from my presentation, they had this question where it's the inverse Laplace of 2 over s squared, and for the answer they put the inverse Laplace but also times u of t. Is that something we have to do or add?
All the times you've been taking the normal Laplace transform, it's technically times u of t. So like if you want, you can multiply this term and this term times u of t, which just means it turns on at t with 0. You don't have to do that, but if you do it, it's not wrong.
Okay, thank you.
You're welcome. There's no more questions about unit step function. We'll call that a day for unit step. I have more examples in the notes, and there's a ton more on the test that I'll send out if you want to see some more stuff, but it's time to move on to the next one. After I erase all the one example of one test that I have.
What? Form.q capital C.
Like they don't do
I can send you after this. I'll try it myself.
The void is going to reach another
Yeah, probably. I just came down. Might have run I did. What? Please make sure. If you have I have an issue on my phone, I can do that. Maybe. You have one here. You? Oh. Sure, this is from extra. Oh, I always have that. I haven't even my phone.
Bro, I'll rent that for you right now.
Okay, I can do the study sheet. Yeah. Yeah, I'm going to actually before we go back to myself. But the prices are maybe yeah, I should be up there. Huh? Yeah.
No,
if it says you supply X prime of X y y X L prime versus the variable.
yes, it's very bad. Those would have I got it.
We got the next topic is separation of variables, but now it's not just for first order ordinary differential equations that you did on your first test. Now we get partial differential equations, which just makes it so much more fun. Because what we're going to be doing now is we're going to be using this. First question I'll ask: who wants to tell me what a partial differential equation is? Is that actually a hand?
Yeah.
Go for it.
You differentiate by one variable.
When there are two variables. Yes. So the idea is this entire year we've been dealing with a function y that the only variable in that function is x. So when we take the derivative, we take the derivative because there's no choice. But now we have some function u that has both variables x and y. So think back to some of those equations that you were dealing with back in, I made 124, where you had to find your dz dx. But instead of doing dz dx, they wrote it as like a curly d, curly x. This is a total derivative. This is a partial derivative. That's what the difference is. Most of you guys probably didn't know that back then, because I only learned it after I was done with 124. But taking a partial derivative, we now have equations that are differential equations, but based on those partial derivatives. So almost every time that you're dealing with this idea of partial differential equations, you're going to have some function u that's dependent upon a function x and a function y. And normally it's just that function x times some function y is your solution. Where that function x is dependent upon lowercase x as its variable, and function y is dependent upon lowercase y as its variable. And that's what all of the bullet points are saying. And then the last thing to note is, how do I take partial derivatives of this u function? Well, I know that u, take the derivative with respect to x, all I have to do is just x prime times y. That capital X prime times capital Y. And if I want to take the second derivative, it's just capital X prime times capital Y. You can see what all the other derivatives are. It's just the same process moving forward. So, on this test, all that we have to do is do the separation of variables parts to set up to, we have to do separation of variables, then we just do some integration, and we find what that u function is. On the final is where the real fun starts, because that is when you have to solve a partial differential equation. And that one question alone is never on test 3, because it can't be on test 3, because that one question will take probably about 50 minutes. Woo! Oh boy. You'll have either the heat equation or the wave equation. I can tell you exactly what the format is, and people will still get it wrong. But, with all that being said, let's worry about separation of variables right now. These problems, well, they do have a lot of steps. I love them because you do the same exact steps every time. And I have those 7 steps written out, step by step, what you have to do for the step, side by side with me doing that actual step to learn for this problem. So if you're good at following instructions, these questions should be good for you. So the first thing that we have to do is, I say step 1 is rewrite the problem using capital Y and capital S. I don't like these curly du, dx, so I'm just going to rewrite it using x's and y's. So here I have a lowercase x times, this is u with taking the derivative with respect to x, which means I'm going to be right up here, so it's going to turn into capital X prime times capital Y. And this right side is just capital X times capital Y prime. Boom, step 1 done. Step 2 says, get the term with x, the capital X prime, by itself. Now in this question, it already is by itself, because this is your capital X prime term, and it's already by itself. So we don't have to worry about that step here, but in some other problems you might have to do that, where you maybe subtract the term over to the other side, or whatever it is for that problem. But we got our capital X prime by itself. The next step is, I want to divide everything by u, meaning I want to divide everything by capital X times capital Y. So I'm going to divide both sides by capital X, capital Y. And you might be asking why. Well, the reason why we do that is because watch how things simplify out. On this left side, I have a capital Y and a capital Y in the numerator and in the denominator, so those cancel out. On the right side, I have a capital X in the numerator and the denominator, so those cancel out. Rewriting what I have is going to give me lowercase x times capital X prime over capital X is equal to capital Y prime over capital Y. And when you look at that, those variables are separated. Cool. So that is step 3. Done. The next step says, and this is some, mathematical, there's reasoning behind this, where if x is only dependent upon x and y is only dependent upon y, the only way that the two of them could be equal to each other is if they're both equal to some constant. And this is where our lambda comes into play. The reason we make it negative lambda because it makes things easier later on. So you could make it a regular lambda, a positive lambda, but then you'd be dealing with more negatives later in the problem. So we set it equal to this constant. We don't know what this constant is, but I know it's some constant lambda. And remember notice how in your eigenvalue problems you have a lambda? Yeah, it's that same lambda. It comes back. Yeah. So now I set everything equal to that negative lambda. And now I really have 3 separate equations. I started off with my x is equal to my y's, but now I can write out new equations where my x's are equal to my lambda, my y's equal to my lambda. So let's do that. Let's break this now out into 2 separate equations. I now have my lowercase x times capital S prime over capital X is equal to negative lambda, and let me change the color. Our capital Y is equal to negative lambda. Once I break this out into 2 equations, I don't like fractions. I want to get rid of the fractions. Let's multiply things over. Let's subtract some stuff so that way I have a first order differential equation set equal to 0. So what does that mean? Take the capital X, multiply it to the right side. So that goes away. We have a capital X here. And then I add it to the left. So I have lowercase x times capital X prime plus lambda times capital X is equal to 0. I do the same thing with my y's. I get capital Y prime plus lambda times capital Y is equal to 0. And the last thing that I want to do is I want to get the derivative terms by themselves. So right here, we're already good. My capital Y prime, it's not being multiplied by anything. But this capital X prime is being multiplied by this lowercase x. So let's divide everything by that lowercase x. So this gives me capital X prime plus lambda over lowercase x times capital X is equal to 0. The 0 divided by x is still 0. So now I have these 2 first order differential equations. Now, these might still not have any clue what to do because you're not used to seeing why do I have a capital X, why is it a capital Y, and some weird upside down Y that's supposed to be a constant. I don't know what's going on. Well, why don't you use another different color? I'm gonna rewrite this equation with my x's. I'm gonna make it look a little bit different. I know that capital X prime is a function. So instead, let's say that function is equal to a y. And I know that the lambda is a constant. So let's say that that constant is 3. So if I have y prime plus 3 over some variable x times y is equal to 0. Does that look familiar? Because you solved that problem like 5 times on your first test using a bunch of different methods. This is just a first order, because we have one derivative, ordinary differential equation. Because all I have is some function y that's dependent upon x. This is the exact same thing as this, just instead, my 3 is just written as this generic constant lambda. And my capital X prime is function x. Instead of it being written as y, it's written as capital X. So what that means is we can go back to all those things we learned on our first test to solve this first order differential equation. So let's do that. So let's start with our y term. This is going to be an even easier one. So it means I don't have this weird, over x term. So I have capital Y prime plus lambda y is equal to 0. The first thing I notice is this is a homogeneous equation, right? It's set equal to 0. I also notice that I have constant coefficients, right? Because I have a 1 and a lambda. And when I have a homogeneous equation with constant coefficients, I can just use my auxiliary equation to get the solution. So I know that's just going to be m to the however many derivatives I have, it's that power. So it's m to the first power plus lambda times m to the 0 is equal to 0. I'm starting to like this one. This is nice and easy. We just get m is equal to negative lambda. And if m is equal to negative lambda, that means that my function, capital Y, is just some constant, so we'll call it C1, e to the negative lambda times lowercase y. Because the function, capital Y, is dependent upon the variable, lowercase y. And that is the solution to this, the equation that's in black. That y prime plus lambda times y equals 0. So that's done. But now we gotta go over here. Now I have just capital X prime plus lambda over lowercase x times capital X is equal to 0. And how can I solve this one? So, can we do it the same way?
No.
No, because I have non-constant coefficients. I have a lowercase x in the coefficient for this second term. So now I need to look at what are other methods coming from the first test. Now the first test, what we always say was the simplest one, the first thing we should check for. Separation of variables. Right? Separation of variables, all that we have to do is be able to take the integral of both sides. Let's see if we can do separation of variables. Where now, one variable is my capital X, the other variable is my lowercase x. So let me rewrite this a little bit, so that way I can make it a little bit more clear. Because this capital X just means the derivative of my capital X function, or in other words, the derivative of capital X with respect to lowercase x, plus lambda over lowercase x times capital X is equal to 0. Well, if I subtract this term over to the right side, then I get d capital X over d lowercase x is equal to negative lambda over lowercase x times capital X. I can now multiply the d little x to the right side, divide the capital X to the left side, and I've separated my variables. Right now I have 1 over capital X, d capital X, is equal to negative lambda over lowercase x, d lowercase x. And when I'm doing separation of variables for ordinary differential equations, I've now separated my variables, all my capitals on one side, lowercase on the other. I just take the integral of both sides. So what's the integral of 1 over capital X?
ln of x.
ln of capital X. And that's going to be equal to, I know this negative lambda is just a constant, so I'll pull that out in front. And now I just have the integral of 1 over lowercase x, which is just going to be ln of lowercase x plus c. It's coming back.
Yeah.
You gotta remember that plus c.
Would it be outside?
Yeah, it's outside. It's inside this. But outside of that. Yeah. So now, I want to simplify this a little bit, so I'm going to bring it over here. Now I have capital X is equal to negative lambda ln lowercase x plus c. I need to get some function for capital X, so I can multiply by capital Y and get my function u that I'm looking for. So I know that I need to have I want to do e to some power will give me just x. But the first thing that I want to do is let me distribute this negative lambda. That's going to make the next step look a little bit nicer. So this is going to be negative lambda times ln of lowercase x plus, or minus, rather, lambda times c. Well, I know that if I have a coefficient times ln of something, I can pull that coefficient up into the exponent of what's inside. So instead of negative lambda times ln of lowercase x, I'm going to make this just ln of x to the negative lambda. So instead of having this negative lambda times ln of x to the 1, I'm taking this and I'm putting it in the exponent. That's our log rules again. Exponent and log rules, we love them so much. So now this x, or this negative lambda, doesn't exist there, it's just in the exponent. So now, since I want to get rid of the ln, I want to just have capital X, I'm going to raise both sides to the e to the power of that. So the left side becomes capital X, the right side e to the ln of x times e to the negative lambda c. So this e to the ln of x to the negative lambda becomes x to the negative lambda times e to the negative lambda c. Does that make sense? Is this line? This line simplifies to e to the ln of x to the negative lambda times e to the negative lambda c. Little. So now, I have a function for my capital X in terms of lowercase x. Yeah. You're saying like this is just another C? They would probably want you to write it as like, if you said this is C2, then make this like this C3, because they want you to know that's a different constant, but yes, you can do that. So we now have this function, capital X, that if you wanted to, e to an exponent that's a constant, it's just another constant. So you could rewrite this whole e term as just like a c, we'll call it c2. Because we know that's just another constant. So now, going all the way back to the top, I know my final answer u is just x times y. So, let's put those back together. U is equal to capital X times capital Y, where capital X is now, we have this constant times x to the negative lambda, this is a lowercase x, times this y term, where I have another constant, but it's just going to get absorbed within that c, times e to the negative lambda times y. You only have to have that one c term in your final answer because the two constants are going to get multiplied together, get absorbed into one constant, and we're left with x to the negative lambda times e to the negative lambda y.
Let me fix this first.
What?
You read it all. If we don't do the C2.
If you keep this at most, they'll take off 1 point. They might like to see that, oh yeah, all the constants combined. But this is your final answer for separation variables. Question? Maybe. I've seen sometime, granted on a test like this where people are going to be probably losing a lot of points, they might be a little bit more lenient with that. But I've seen on other tests where if you don't simplify constants in BSC, you can still take off here.
Not having to worry about it. It doesn't waste time.
I did it on Tuesday. That's
not even have time to focus on the X time.
This problem is my first one that it's simply it's all the big things. All the items.
Yeah. Yes.
Exactly.
Yeah. These are, this is little x and little y.
Eigenvalues and
So the question of separation will move on to Fourier's
I always write something up.
yeah, because then it's just like you just be screaming and that's all you
I think this
Hey, question.
Yes.
Is the C constant value like going to be obviously distributed to the X as well as
yes. This is C1 times C2.
okay, thank you.
Yes.
With getting rid of ones and negative lambdas affect how you solve it by putting it in C2?
Same with the negative lambda effect with these.
If you absorb it into the constant, that's how you solve the negative lambda.
Shouldn't. I'm thinking about how you have to solve the problem. I think you find plugging your lambda values first and then find your C1, C2 at the end.
Yeah.
So, because the lambdas depends on calculus, you find out you don't have to worry about this in the final. But your lambdas you find from your boundary conditions, your C's you find from your initial conditions.
Yeah.
But you solve the boundary conditions first. So you plug in the lambda, and then in order to make it equal to the initial condition, the C will adjust based on what your lambda is. That sounds weird, you don't need to know what it just meant, but
Invoking effects.
we'll see it on, yes, the C will change depending on the lambda. You'll see that very much.
I was listening to it.
We're going to start it. So, Fourier series, pretty much everything you need to know in order to solve a Fourier series problem is either there or right here. I mean, you also need to know how to take the integrals, which ends up being one of the hardest parts. But this is all that there is to it. Basically, the Fourier series, which is that common equation f of x, is equal to 1/2 a sub 0 plus the summation from n equals 1 to infinity of a sub n times cosine of n pi x over L plus b sub n times sine of n pi x over L is an approximation of the Fourier series. And what it is it's a way that you can represent any function by using a sum of sine and cosine terms. Yes.
Will we be getting a table of integrals on the exam or no?
Nope.
Let's see. Yeah.
I don't see on past tests. So that either means that they weren't scanned and sent to me, or you don't get it. Oh, I see. On one of them, I see table of integrals.
All right.
So if you need it, then I'll assume you have it. If you have, if they give you anything that's super weird.
Is that journal formula?
No. You don't get any of these formulas. The only thing they'll give you is table of integrals, maybe, and Laplace Transform.
Integral cosine x.
But these are the equations that we need to know. So you see that our A sub n term, is that, I wrote these all in their generic form. I know most of the time we do that like 2 over L when we go from 0 to L. But these are the equations that we have. We have our A sub 0, which we know is slightly different. But you can just remember that A sub 0 is the same thing as your A sub n term when you plug in n equals 0. Because when I plug in n equals 0, cosine of 0 goes to 1, and it's the same exact equation. But this is what we have. Remember those formulas. And the way that the question is going to be asked is they'll give you, most of the time, a piecewise function of 0 to some number, normally either 2 or 4. And they'll say, what are the first 4 terms of the Fourier sine series or Fourier cosine series of this piecewise function? And it's your job to reflect it either evenly, which means over the y-axis, or odd over the origin, so that way it becomes either a sine or cosine Fourier series. How do we do that? Very good question. We'll do that in this example problem. Do you have a question?
Yeah, do we have to graph it as well?
Yes, most of the time we'll have you graph it. We're going to graph it at the end. But most of the time these problems are broken out into find the Fourier series of the function, and then part B is sketch the function to which the Fourier series converges over some interval. So, the problem that we will work with is from spring 2017, question 4, and it is f of x is equal to x between 0 and 1, and it's equal to 0 when 1 is less than or equal to x, which is less than or equal to 2. And the problem says it wants us to find the first 4 non-zero terms of the Fourier sine series. So, I know that it's saying find the Fourier sine series, so I'm going to be using my B sub n terms, because those are the ones that have the sines in them. So when I ask for the Fourier sine series, those are the ones that I'm using. So, where do we start?
Get your A sub O term.
In a Fourier sine series, we don't have to worry about A sub O, because I know that all of my A terms are going to go to 0. If it had asked for a Fourier cosine series, then that would be the first step.
Find the L.
Find the L. I like that, because in anything we do, we need to know what L is. So in this problem, what is L going to be? It says that L is the total length of the section. It's defined from 0 to 1, from 1 to 2. So what is L?
2.
L is 2. Boom. We got one other question. So I know that I'm doing Fourier sine series. So I know that I'm going to be using my B sub n terms. So let me write down this B sub n terms.
It's that question about like the technicality.
I have 1 over L, integral of negative L, L of f of x, sine of n pi x over L, d to s. So I want to figure out what is B sub n. So let me start plugging in stuff that I have. So B sub n is equal to 1 over 2, the integral from negative 2 to 2. My f of x is just x, times sine of n pi x over 2 times dx. Now, you could leave the integral like this, but if you want to save yourself a little bit of time, we know that this equation, that this function is going to be symmetric about the origin, because we're doing the Fourier sine series. And I know that we're making it symmetric about the origin, so that way it's an odd function, so that way it only contains sine terms. So what does that mean? It's symmetric about the origin. That means the integral from -2 to 0 is the same thing as the integral from 0 to 2. So instead of doing the integral from -2 to 2, I can say that it's 2 times the integral from 0 to 2. So I can just pull this 2 out and then just put it in the numerator out front. So you can have 2 over L times the integral from 0 to 2 of the x sine then by x over 2 dx.
Can you say that again?
So all I did was, instead of from -2, I started off with 1/2 of -2 to 2. But instead of doing the integral from -2 to 2, I'm going to do the integral from 0 to 2. And it's going to be 2 times that. So it's going to be 2 times the integral from 0. Yes.
Is that the same? The same thing?
Yes. If this problem had asked for the first 4 terms of the Fourier cosine series, you would have done the same thing. Yes. The question says find the first 4 non-zero terms of the Fourier sine series for x. Well, oh, right. So, one thing that I'll correct myself on is if I go on the integral from -L to L, it's fx.
Yeah, that's
right? Because I don't have one function from 0 to 2. But what I can do is I can break this out into a sum of integrals, right? From 0 to 2, this is really the same thing as 2 over 2 times the integral from 0 to 1 of x times sine of n pi x over L dx plus 2 over 2, the integral from 1 to 2 of 0 times sine of n pi x over 2 dx. Right, because over the bound 0 to 2, I don't have one set integral or one set function. It's x for 0 to 1 and 0 from 1 to 2. So, but I know that when I have this second term, it's just 0. So this whole thing is going to end up going to 0 anyway. So the only term that I'm really worried about here is this 2 over 2, which is just 1. The integral of 0 to 1 of x times sine of n pi x over 2 dx. And that's going to be the integral that we're working with for this problem. But now I need to integrate that. And that is not on my integral table. So how do we do it? Integration by parts. How do I know that's integration by parts and not do substitution? Well, I know that I do integration by parts when the derivative of one of the terms becomes much simpler. And I know that the derivative of x is just 1, which is much simpler. So, I know that I can make this u term that x. So u is equal to x because I set u equal to the thing that when I take the derivative, it becomes much simpler. Which means that du is equal to dx. And that means dv is equal to everything else. So sine of n pi x over 2 dx, which means v is the integral of that. And I know the integral of a sine term is just negative cosine, so it's negative cosine of n pi x over 2. This just so it doesn't get in my way. But I need to account for the fact that this inside these parentheses isn't just x, it's some coefficient of n pi over 2 times x. So in order to account for that, I now need to divide by that coefficient of n pi over 2. Or I can just multiply by the reciprocal, 2 over n pi. So if I were to take the derivative of this v term, I pull the constant down in front, derivative of a negative cosine n pi over 2 is positive sine of n pi over 2 times the derivative of what's inside, which is n pi over 2. That gets multiplied by this coefficient to just become 1. And I'm left with only the sine of n pi x over 2. Now that I have this written out, I can say that this integral, so the integral of u dv is equal to u v minus the integral of v du. So I can rewrite this as u times dv, which is x times sine of n pi x over 2, u dv, minus the integral of v, which is negative 2 over n pi cosine of n pi x over 2 dx. What? You're right. This should not be sine x, it should be u v. And v is this. So it should be x times v. So I'll pull this negative 2 over, I'll pull that coefficient out in front, negative 2 over n pi times x times cosine of n pi x over 2. So we now have u times v minus the integral of v du. And now this 2 over n pi I'll pull out in front just so that way, because I know it's a constant. So I'll make this a plus 2 over n pi times the integral of cosine of n pi x over 2. So I'm just going to rewrite that. We have negative 2 over n pi times x cosine of n pi x over 2 plus 2 over n pi, the integral of cosine n pi x over 2 dx. So now I need to take the integral of this cosine term. Well, the integral of the cosine of n pi x over 2 is just going to be positive sine of n pi x over 2, again times that 2 over n pi. So when I bring this down, I can just make this a 2 over n pi squared. And then I bring down everything else that I have with the negative 2 over n pi x cosine of n pi x over 2. And all of this I can now evaluate on the bounds from 0 to 1. And I'm plugging those in for my x values. So when I plug in my 1, I get negative 2 over n pi times 1 cosine of n pi over 2 plus 2 over n pi squared times the sine of n pi over 2. All of this minus when I plug in 0, which will be negative 2 over n pi times 0 times cosine of 0 plus 2 over n pi 1 squared times the sine of 0. And you can see that this whole second term, this becomes 0 because I'm multiplying by 0. This becomes 0 because I have the sine of 0. So this whole second term goes away, which is very nice because I don't want to deal with all that stuff. And we're left with just this. And this is our b sub n term. Great. Now, if you can, you want to try and simplify it down a little bit, just to save yourself some time in the next steps. But there isn't really much we can do to simplify this down. Maybe you can factor out a 2 over n pi, but that's not really going to do too much for you. But now, we have to do what the question's asking us to do, is find the first four non-zero terms of the Fourier sine series. So what that means is we start off by looking at, I'll bring that back up in a second, but we're looking at up top that f of x, where the 1/2 a sub 0, I know that's 0 because I'm doing a Fourier sine series. That summation of a sub n cosine of n pi x over L, those are all 0, so I can ignore that. I'm now looking at my b sub n sine of n pi x over L terms. I want to find the first four of those, so I'm going to start by plugging in n equals 1, because that's where my summation starts. Figure out what b sub n is, and then multiply that by sine of n pi x over L. Then do n equals 2, n equals 3, n equals 4, and keep going until I get 4 terms that aren't 0. So, let's do that. We have our b sub n, and I'm going to say, when n equals 1, what happens to my b sub n? Well, I know that I'm going to have this whole term is going to be negative 2 over pi, negative 2 over pi, times cosine of pi over 2, plus 2 over pi squared, sine of pi over 2. What's the cosine of pi over 2?
0.
0. Because we know that if we look at our unit circle, I know that the cosine is my x value. At pi over 2, I'm right there. So the cosine term goes to 0. My sine term goes to 1. And I know that my b sub 1 is just going to be equal to 2 over pi squared. All this freaking work just to get a 2 over pi squared. Great, right?
It should be
So now, we gotta do the same thing until we get 4 terms that aren't 0. So now let's go n equals 2. And I'm going to be plugging n equals 2 into this whole thing. So this is now going to be 2 over 2 pi times 1 times, so we have negative 2 over 2 pi times the cosine of 2 over 2 pi, so just the cosine of pi. And then this next term, I'm going to have the sine of pi. And what's the sine of pi?
0.
0. So I know it's just going to be plus 0. And the cosine of pi is negative 1. So this whole thing, the 2 over 2 just becomes a 1. So this just is 1 over pi. Negative 1 and negative 1. This whole thing just becomes 1 over pi is b sub 2. And we can do the same thing for n equals 3 and n equals 4, but at the same time, I'm just going to write out what they are. So n equals 3 is going to be negative 2 over 3 pi squared is b sub 3. And then when we do n equals 4, we get b sub 4 is negative 1 over 2 pi. And I take each of these terms and I plug them into this b sub n sine of n pi x over L. Yeah.
Why is there no b sub 0 term?
There is no b sub 0 because that summation starts at n equals 1.
Yeah. All right.
So since the summation starts at n equals 1, all we're doing is writing out the terms of that summation. So I'm starting with my n equals 1, because that's what that sticky notation starts at. So now, all I have to do is take these coefficients, multiply them by that sine of n pi x over L, and I'm done. So f of x is equal to b sub 1, which is 2 over pi squared, times sine for this term, n is 1, so it's 1 pi x over L, which is 2, plus b sub 2, which is 1 over pi, sine of 2 pi x over 2, minus 2 over 3 pi squared, sine of 3 pi x over 2, minus 1 over 2 pi sine of 4 pi x over 2. And this is the answer to our problem.
Sounds like fun.
Yes.
Yeah, that's like 15 minutes.
Do your best. So someone asked me, would I recommend doing all the problems partially, or like doing like 3 of the 4 fully and just kind of taking the L's for it? Like, if you know 3 topics really, really well, then put the time onto those topics, and whatever time you have left, do the last one. But if you're confident on all the topics, try all the problems, because for all you know, one of them might be really easy that you can get done in 5-10 minutes, and then you'll have more time for the others. Like this problem right here, if you think about it, if you knew what you were, if I knew what I was doing and I wasn't walking all the time through every step, I could do this. There aren't that many steps. All we did is we wrote out our B's and N term, which turned into that integral. We took our integral and integrated it parts. Once we took our integral, we plugged in our bounds, and we just plugged in 1, 2, 3, and 4. So if you're confident you know the steps for it, it doesn't take that long. Yeah. So the question is, how would this change if you have to do a half-range expansion? It would actually change absolutely 0, because this problem is a half-range expansion. I didn't write it down, but the problem actually, the word for word, what the problem said was, find the first 4 non-zero terms of the, and then kind of right here is like this parentheses, half-range for your sine series. Because the region is only defined from 0 to 2, but you say, well, I know that the function does this. But since I want my sine terms, I want this to be a sine series, I'm going to make this an odd function, which we did without you guys even realizing it. By choosing only to use sine terms, I said, let me expand this to be an odd function, which means that it's featuring reflecting over the origin. So it looks like this. This is before your sine series from -2 to 2. Now, what the last part of the problem will say, it's going to ask you to graph it from -6 to +6. And what you have to do for that part of the problem, you guys are going to want to know, and everyone always messes up on this, is the 2 biggest things that you have to know. We have this defined from -2 to 2. All I literally do is copy and paste. So -6, -4, -2. I copy this and paste this. So from -2 to -1 is the same thing as -6 to -5. Then it drops down. It looks like that. That's an open circle. This is a closed circle. And it goes like that. And then you do the same exact thing, copy and paste for the region from 2 to 6. So, and the one thing that everyone always messes up on is at these points where you have a jump, it converges to the midpoint of that jump. So right here, it jumps from 0 to -2. You do an open circle down here, you do an open circle up here, and you do a closed circle at that -1 point. Because it converges to -1. Yes.
So the open circles are required? Or
Open circles aren't as necessary, but you definitely need to have that closed circle at that midpoint between the 2. Yeah.
Is half range the same as half series?
I haven't ever heard it called half series, but I'm going to say yes.
Okay, because like on our test also, like it says exam 3 does not include the topic of half range expansions defined on the interval 0 to L. What is that?
What is this?
Like it doesn't include, but like, is that any of this?
Does it say it's going to include Fourier series?
Yeah.
Fourier treatment series.
So,
That was like,
so it won't include half-range expansion on the range from 0 to L.
yeah.
So what that means is this exact type of problem where we did this won't be on it, but you'll have something where instead, where it won't be a half range, you're going to be given a piecewise function that's defined on like -2 to 2. And it's going to be, you're not going to be able to do this part where you do the integral from 0 to 2, because it's not going to be symmetric necessarily. You have to do the full integral throughout the whole thing. But the good thing is then I don't think they're going to ask you to graph it, because I feel like that's more difficult to do if it's not a half-range expansion. Because this problem is a half-range expansion. We were given it defined from 0 to 2. It's half our total range of -2. And we expanded it to that full range. But what I'm assuming they're going to give you now is they'll give you a piecewise function from -2 to 2. And you just have to break this up into 4 integrals. Most of them will probably be relatively easy. Yeah. Can they ask you to use both sine and cosine? Yes. Do I think they will? No. Just because then you're not going to take 2 integrals and that just takes a lot of time. But then again, as I'm saying that, last semester on their test, they did have to use both. So, one thing to note, so to answer your question more specifically, look at, when I send these out, look at the spring 19 exam, because they had a function that was defined from -4 to +4, and it just said find the Fourier series for the function. It didn't say find the first 4 non-zero terms of the Fourier sine series. It just said find the Fourier series, which means you have to use both A and B terms. So it's the same exact process that we did. Just you have to do your base and then find your cosine terms plus your base and then find your sine terms. Yeah. How do I know how to graph it? So you just graph this on a region that they give you. In this problem, we knew that it was a half-range sine series, so we reflected it over the origin. Because a sine series will be reflected over the origin, but you won't have to do that over that. And all we did was copy and paste. I copied this region and pasted it right here. And then you also have to do from +2 to +6, and you copy and paste. Yeah.
So this problem is the actual Fourier series is going to be just solve for each.
Well, we did. We plugged it in right here. This is our B sub n pi side of n minus 1.
It asks what the Fourier series is, and then
you would just take your A sub n term, or you take this B sub n term that we got the top. You would take your B sub n term and say, you would be able to simplify down the problem like simplify down to 1 term, and you would just plug it down to that for your A sub n. Simplify it. And we find the A sub 0 and now you have to clear up that, you just plug it right to that. But in this case, you just thoughts that only with our That's a case of your A terms are only used when it asks for a cosine series, but if it asks for the full Fourier series, you have to do both your A sub 0 and A sub n and your B sub n. Yeah. So if it asks to be cosine, the only thing that will be different is a cosine's an even function. So instead of reflecting it over the origin, we're reflecting over the y-axis. And it would look like this. And then you just copy and paste that. Any other questions on this before we get eigenvalues of my standard one? Last one.
Yeah, so I actually have access to the product already. That sort of thing, that's kind of like continuing on. Learn to keep I think this semester is actually just sat there like picking up for 10 minutes. It would be really fun. They handed me a sheet. They gave me the worksheet. I took a picture and sent me a friend who was playing the class late. Like, here's your worksheet from the rest of the day. And I was like, what? You're not in the rest of the day. I was with
Yeah, it is. Okay. We got our last one. We got some eigenvalues. We'll look at what we get out of this really, really hot room. So, we got eigenvalue problems. And this is pretty much how it's going to be set up. It's going to say, here's an equation. It says, find all eigenvalues and corresponding eigenfunctions for the boundary value problem that. and you'll have something very similar to this. It's going to be a second order equation. There's going to be a lambda somewhere in there, and yes, this is the same lambda that you had from your separation of variables. When you're doing your partial differential equations later on, they'll all come together. We have a y double prime plus lambda minus 3 times y is equal to 0. And again, the idea is lambda is some constant value. We just don't know what constant value it is. And that's going to be the really annoying part of this problem. But we need to solve this problem, right? So what's the first step of solving a differential equation? Solve the homogeneous, right? So let's still do that. So I know that this is going to be m squared plus lambda minus 3 is equal to 0. So I can move this over to the other side, and I get m squared is equal to negative lambda minus 3. Or you could write that as 3 minus lambda. And I take the square root of both sides. So I get that m is equal to plus or minus the square root of 3 minus lambda. Cool. So I now have my solution to my auxiliary equation. So now I try and write out my homogeneous solution. But there's 3 forms of the homogeneous solution, right? There's if we have repeated roots, if we have non-repeated real roots, and if we have imaginary roots. So which one is this? All 3. Well, we don't know. Because, what if, we don't know what lambda is, right? Say lambda was 3. Well, then I have 3 minus 3, which is 0. I get plus and minus 0. Now I have repeated roots. Say lambda was 10. Well, now underneath the square root, I have 3 minus 10, which is square root of negative 7. Now that's imaginary. Say lambda was 0. I now have square root positive plus and minus square root of 3. I now have non-repeating real roots. That's my third case.
Wasn't there another one where you had lambda in the homogeneous
What
problem where you had lambda?
Yeah, that was in your separation of variables. But that was the first order. And because it was first order, we didn't have m squared, we didn't have to take the square root, we didn't have this problem. But we got a problem. So I know that there's 3 possibilities for what this format could be. One could fall in 3 cases. That's where it comes from. And if you guys remember, on the first test, when we were doing the homogeneous equation, I said you could have this case 1, case 2, case 3. Remember this because it's going to come back to haunt you. Well, it's time to come back and be haunted. The first thing that I'm going to look at is I'm going to look, so case 1, I'm going to say, I'm going to look at everything that's underneath this round, so that whole 3 minus lambda. And let's pretend that that 3 minus lambda is equal to 0. So 3 minus lambda is equal to 0. That means m is equal to plus or minus the square root of 0, which means m is equal to 0 with repeated roots. And if I have repeated roots, then I know that my y homogeneous, or my y, is going to be c1 e to the 0x plus c2x e to the 0x. And I know e to the 0x is just going to be 1. So this y just becomes c1 plus c2x. But now I want to find what those c1 and c2 are. So I want to see, is there a solution to this problem? Well, now I can plug in those boundary conditions. We plug them in the same exact way as we would initial conditions. So I know that I have my y already. Let me take the derivative of this so I can plug in that second condition. So y prime, nice and easy, is just c2. So when I plug in my y, I plug in 0 for x, y is equal to 0. I get 0 is equal to c1 plus c2 times 0. That goes away. 0 is equal to c1. And I go to my second case, and I have 0 is equal to c2. And c1 0, c2 0. This tells me absolutely nothing about lambda.
Right.
Which means I have no eigenvalues and no solution. So it's a trivial solution, but there are no eigenvalues, which means there's no eigenfunctions, which means we're sad. We don't have an answer. But it really means we're happy, because if there was an answer, that'd be more work for us. So I did case 1. I said, what if I had repeated roots? Well, now let's look at the next case, and let's say that with case 2, let's say that this 3 minus lambda is equal, it's a positive number, it's greater than 0, because this will give me real roots. And I want to set it equal to something just so I can make it a little bit easier. So I'm going to say that this 3 minus lambda is going to be equal to an alpha squared. Because whatever alpha is, I know that when I square it, it's a positive number. Right? Because anything, you take a positive number, a negative number, you square it, it's positive. The only restriction is that alpha can't be 0. Because if alpha is 0, then we just have 3 minus lambda 0 and we're back in case 1. And we already did case 1. So I say 3 minus lambda is equal to alpha squared. I now jump back and plug that into my auxiliary solution. So m is equal to plus or minus the square root of alpha squared, which means m is equal to plus or minus alpha. I plug that into my solution for the homogeneous, but now I have non-repeating roots. So this is going to be c1 e to the alpha x plus c2 e to the negative alpha x. And if you notice, we're following the same exact step as case 1. Once I plug in my initial assumption, I solve for my m, I plug that into the solution. Now I'm going to take the derivative and then plug in the boundary values. So let's take the derivative. Y prime is going to be the derivative of this, derivative of e to the alpha x is just e to the alpha x times alpha. So it's alpha c1 e to the alpha x minus alpha c2 e to the negative alpha x. I plug in my boundary conditions, so I know y is 0 when x is 0. So c1 e to the alpha times 0 plus c2 e to the negative alpha times 0. My e terms will still go to 1, and this tells me that c1 is equal to negative c2. I take that along with my second boundary condition, and I know y prime is equal to 0 when x is equal to pi. So I have 0 is equal to alpha c1 e to the alpha times pi minus alpha, for c2 I'm just going to plug in negative c1. So we have negative c1, change that minus to a plus, e to the negative alpha times pi. So now, let me move one of these to the other side. So I have negative alpha c1 e to the alpha pi is equal to alpha c1 e to the negative alpha pi. So what can I do to start simplifying this? Well, I know that I have alpha on both sides, those can cancel out. I have c1 on both sides, those can cancel out. And what I'm left with is negative e to the alpha pi is equal to e to the negative alpha pi. And when you get to this stage, this is mathematically incorrect. Because I know that a positive e to some exponent can never give me a negative number. No matter what that exponent is, it's just going to either be a really big number or a really small fraction. So if the left side is negative and the right side is positive, this can never be true, which means, again, I have no eigenvalues. And now, Case 3 is the fun one. Because now I'm going to say the opposite. What if 3 minus lambda is less than? So now I'm testing my third case in which I'm going to have imaginary. So I want to set this equal to some negative number. So what if we just set it equal to negative alpha squared? If alpha squared is always positive, then negative alpha squared is always negative. So now I do the same step. I have n is equal to plus or minus the square root of negative alpha squared, which means n is equal to plus or minus alpha times I. And I know that my y, I know that my y is going to be equal to e. I really have a 0 out in front right here. So it's going to be e to the 0x times c1 cosine of alpha x plus c2 sine of alpha x. And I know that this e to the 0x is just going to go to 1. So I'm left with y is c1 cosine of alpha x plus c2 sine of alpha x. Just like I did in my other steps, now I'm going to take the derivative. So I have y prime. And this is going to be the derivative of cosine of alpha x is going to give me a negative sine of alpha x times alpha. So it's going to be negative alpha c1 times sine of alpha x plus alpha c2 cosine of alpha x. And now I have a question.
What is e raised to there that you crossed out?
E to the 0x. Because the 0 comes from, this is 0 plus or minus alpha. So we now have y is equal to this stuff, y prime is equal to this stuff, plug in boundary conditions. It's the same steps for all 3 cases. So I know that y is equal to 0 when x is equal to 0. So I have c1 cosine of 0 plus c2 sine of 0. Well, I know that sine of 0 just goes to 0. I know that cosine of 0 goes to 1. So therefore, 0 is equal to c1. I go to my y prime. I know y prime is 0 when x is equal to pi. So I have negative alpha c1 sine of alpha pi plus alpha c2 cosine of alpha pi. But I already know that c1 is equal to 0, because that whole first term goes away. So I'm left with 0 is equal to alpha c2 cosine of alpha pi. And I know for this to be true, I need to have either alpha, c2, or this cosine term be equal to 0, right? In order to multiply them together, one of them has to be 0 in order for it to equal 0. I know that alpha can't equal 0 because, although I didn't write it here, if alpha equals 0, I'd just be back to my case 1. I don't want it. So that's not going to help me. If I set my C2 equal to 0, then I'm at the situation where I again have no eigenvalues and I just wasted a lot of time in this problem. So I'm going to take a guess that that C2 probably isn't going to be 0. Which means in order to get some answer for this problem, I somehow need 0 to be cosine of alpha pi. So how can that be true? Let's take a look at our unit circle. I need to figure out what values can alpha be, so that way cosine of alpha pi is equal to 0. So in order for the cosine of something to equal 0, question?
You're assuming alpha is a whole number though, right? Because to make sine 0.
Yes, yes. Well, because, are you saying because I crossed off right here? Well, this is because C1 is equal to 0.
Oh, okay.
So I know that alpha C1 is 0 because C1 is 5. But alpha will be, no, not necessarily. So I get to this step and I need to say what needs to go in here for my cosine of something equals 0. I cross these off because I know that alpha can't be 0 and C2 can't be 0. So in order for this equation to be true, my cosine has to be, the cosine term has to be. So I look at my unit circle, and in order for cosine to be 0, I know that I need to be up here, or down here, or back to the top, or back to the bottom. So I look at what are the values that go inside here. Well, I know this is pi over 2. This is 3 pi over 2. If I come back around, this is 5 pi over 2. This is 7 pi over 2. And I can keep going. But what you should notice is it's an odd number times pi over 2. So I know that in here needs to be an odd number times pi over 2. So we need to find some way that we can represent every odd number. And a very common way to do that is you can say that you have 2n plus 1 over 2 for n is equal to 0, 1, 2, dot, dot, dot. Because if I plug in 0, I get 2 times 0 plus 1, which is 1 over 2. And I get 1/2. I want to divide by.
No. Yeah, you don't divide by.
Yeah. I know that it needs to be 2n plus 1 over 2 times pi. Because this, when I plug in each value of n, will give me pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and all the other values that will make that cosine 0. So I know that cosine of this, 2n plus 1 over 2 times pi, needs to be equal to, because this will make it 0, needs to be equal to this cosine of alpha pi. In order for cosine of alpha pi to be 0. So therefore, I can say that these things that are inside my cosines are also equal. So I know that 2n plus 1 over 2 times pi is equal to alpha pi. We can divide out pi's because we have them on both sides, and I get that alpha is equal to 2n plus 1 over 2. Cool. I'm making progress. But in this problem, I don't really care what alpha is. I literally made up alpha right there. I just said, let's pretend we have this value alpha that when you square it and you negate it, it's equal to 3 minus lambda. The thing that the problem gave us is lambda. That's the eigenvalue that I need to find out. So, I know what alpha is. I can use this equation to bring them back together. So I can say that, well, alpha is 2n plus 1 over 2 for all values n is equal to 0, 1, 2, dot, dot, dot. Well, I know that I need to square it, and I need to negate it. So that way, I now have this equation. Because negative alpha squared is equal to 3 minus lambda. So I can now replace negative alpha squared with 3 minus lambda is equal to 2n plus 1 over 2 squared. And I'm trying to find what lambda is, so I subtract 3 and divide by negative 1. So we get lambda is 2n plus 1 over 2 squared plus 3. And so this right here, you need to make sure that you write this for n equals 0, 1, 2, ... This right here represents your eigenvalues. Okay, give me 1 second. Yes.
So, looked on the wall, it seems like case 3 is the most structured one. Why do you start case 1 if you're going down? Why?
Because you have to use all 3 cases. So the question was, in 99% of the problems you get, case 3 is where all the action's going to be. Why do we have to do case 1 and case 2 first? Because you have to prove that there's no solutions in those first. Because every once in a while, normally in case 1, I believe, you could get a constant solution where, like, you'll get something like C1 equals 0, but you learn nothing about C2, which means you could have a solution y is equal to C. And that's technically a solution, but you get no eigenvalues for it. And you need to show that.
So you have to go in front of
You don't have to go in this order. If you want to just start with case 3, thinking, I don't have time for everything, let me get the bulk of the points, start with case 3, but to get full credit, you have to show all 3 cases. No. You'll get would have eigenvalues in all 3 cases. So we now have these as our eigenvalues. But the problem says find all eigenvalues and their corresponding eigenfunctions. So what do we have to do to get those eigenfunctions? Only I have functions that represented the answer of my equation. And it's right there.
So close and so far.
So I know that in here C1 is equal to 0, so I can make that 0, and I know what my alpha is equal to. So my eigenfunctions are y is equal to C2, which I'm now going to write as C sub n, because that C is going to change for every value of n that I plug in. So it's y is equal to C sub n times sine of alpha, which is 2n plus 1 over 2.
Yeah, it's 100%.
Times x.
Please just get through.
And these represent, you still have to write this for n equals 0, 1, 2, ...
Get on top.
These are all of your eigenfunctions for those corresponding eigenvalues. So now, just so you guys have some understanding of what the hell eigenfunction and eigenvalue even means, what this is saying is if I took n equals 0 and I plugged it in right here for this, I would get lambda is equal to, this would become 1/2 squared would be 1/4 plus 3, this would be 13/4. If I took n equals 0, I got 13/4. And I took that lambda equals 13/4, and I plugged it in to the lambda that we started with, the solution to that differential equation would be this right here when I plug in n is equal to 0. So I now have an infinite number of solutions to that differential equation based on any value that lambda could be. Does anyone have any questions? If you do, come up to me. I know it was long. Thank you for sticking with me. Have a good night.